Hello, everyone. This is Syed Irfan Arifin, one of the authors of this paper. And the title of the paper is Agent-Based Fog Architecture Using NDN and Trust Management for IoT. I'm going to present this paper in this conference, TENCON 2019. So before we get into the discussion of this paper, we need to know what is Internet of Things. So the Internet of Things, or simply IoT, is basically a system of interrelated computing devices or mechanical or digital machines, objects, animals, or people that are provided with a unique identifier and the ability to transfer data over network without requiring human to human or human to device or human to computer interactions. In this IoT paradigm, each and everything is basically uniquely identifiable, and it has to be connected to the internet. Now, since the number of IoT devices are increasing, and we are using that on a daily basis in our home and in any smart places, in a smart office, or even in traffic jams with smart signals, or in our home with smart Wi-Fi devices, and so on. But another crucial thing that is getting hampered or will be hampered soon by this increasing number of devices, and that is the network. Because the number of devices, when the number increases, the number of devices increases. Of course, each and every device will be communicating with some sort of server or among them, and that will increase the usage of data. So if we think about uh, from two perspectives, one is the cost, because each and every data is going to cost us or the company or anyone who will be using that. So the lower the data consumption, is the better. And another thing is, even if we are ready to go for the cost, there are also issues involving the network congestions and also the high volume data usage by these IoT devices. So in this paper, what we try to do is we try to propose a new network model, a new network infrastructure through if it's been implemented with Internet of Things devices. In that case, the network consumption will be significantly lower than the one we already have. So before we get into that, into explaining how this infrastructure is going to work, we need to overcome or we need to know some basic terminologies for this infrastructures. All right. So now we're going to talk about named data network. So named data networking, or NDN, is basically a content-based networking architecture, which is considered to be the future internet architecture. We don't know about that, but the idea of NDN or named data networking is pretty intriguing. I mean, the way we traditionally use the network is basically a host-centric IP-based architecture, but this one is basically a name-based identification network. In NDN, we have two types of packets: an interest packet and a data packet. The interest packet actually contains the content name, selector, nonce, and etc. The data packet contains the content name, signature, signed information, data, etc. The package forwarding contains CS, PIT, and FIB. CS is basically content store. That is something which is used by the nodes, and what they do is they cache the data, that data requests. And for the PIT, that actually stands for pending interest tables, that has all the records of the past requests which has been forwarded to different interests or the sources that the data needs to be delivered. And the forwarding information base, or FIB, is dedicated routing protocol which transfer interest packets. And another thing is the NFD, that is the Indian forwarding daemon, that runs in nodes. And if the requested packet is not cannot be served by that node, the NFD actually forwards the packet to a different node where it is where it can find its purpose. So using NDN in this infrastructure is basically one of the best thing that we have decided to do, and the reason is that with NDN, we can actually have the trust management problem solved. I mean, the trust management. What is the trust management problem? The trust management problem is, let's say there is a device and it wants to receive some information like a temperature data from another device. So it wants to receive the today's weather temperature data actually. So when the device provides the data, I don't know whether that device is reliable or not, or if it's not actually a device rather than a hacker trying to feed me some wrong information so that I heat up the room heater and then he can get in to do some bad stuff. So that's basically the trust management problem. So using Indian, there's going to be more of a the trust certificates can be released by each and every devices, and when we are setting it up with our account, we can actually have uh, trust certificates issued to each of the devices, and that's how we can tackle the trust management problem with NDN. Now let's talk about the IoT infrastructure with computing. Uh, we have divided the whole data communication into four levels of abstractions. As you can see that the lowermost level contains all the IT devices, and that can be from different regions. And the uppermost level is the main cloud service, and the middle two layers are basically there to support the whole data transfers. So the second layer, the second low layer, which is the SOA layer or service oriented architecture layer, uses the service composition from service oriented architecture to compose complex services from simple services. For an example, let's say one of the IoT devices is asking for weather updates. Weather is a service, and it's made of a very simple services like one can be humidity service, second can be the temperature service, third can be the UV index, which can be which can be used in other services too. So the SOA actually combines all those three services into one and feeds it back to the IoT device. And that's like one of the cool things about this infrastructure is that you can use one service in different complex services. And the agent-based service-oriented architecture layer uses some machine learning techniques to identify, update, and store important services. I mean, frequently requested services are to be identified and regularly updated in this agent-based SOA layer. The significant part of this infrastructure is this one, the agent-based SOA part, that we're going to talk about next. Now, let's explain the agent society. Uh, the agent layer, the SOA agent layer, we are calling that an agent society because it's actually made up with two agents. And one is a checker agent, another one is the update agent. The checker agent usually transfer data to end devices from the CS or the PIT, and the update agent is a prediction based NFD. The prediction here is done in Azure Machine Learning Studio for our convenience, but later when we progress, we may change it to a more convenient thing so that it can be used across different platforms. And we use knife bias to determine service priority in a given specific region. To test our environment, we actually need a lot of nodes, but which is quite inaccessible for us to right now or the time of testing. So what we did is we used three virtual machines in different geographically positioned data centers in Microsoft Azure, and each virtual machine represented a different node. And these nodes were in different regions, and we made sure that they communicate over the public IP. That's how we can ensure that it's not using any special benefits given by Microsoft Azure like VPN or anything or private networks. So using the public IP, we'll get the worst case results. And we were running Ubuntu 18 LTS in all the nodes, and we used JNDN to implement the NDN in those nodes. And we used randomly generated data to to do the communications, and later that data set was used in Azure Machine Learning Studio to do further comparison. Now let's talk about the comparison. What we did is we recorded the data input, data in and data out on the network interface cards of those virtual machines. And as you can see, that total 7.63 megabytes were consumed by a traditional infrastructure, and we use those same requests in our proposed model, and that consumed around 1.55 megabyte, which is significantly lower than the traditional one. Let's talk about the efficiency of our infrastructure. So what we did is we compared both results with different numbers of requests made by different IoT devices, and as you can see that at the number if the number of requests if the similar number of requests increase, then the data consumption in the upper layers goes down, which actually is the main target here. I mean, when you are using that, let's say in a home environment, in that case, let's say in a neighborhood, uh, one or two SOA or agent-based SOA will be running, and that will be limiting the data usage and giving the same quality of service. And that will also reduce loads in the main cloud service. And for our future work, we would like to say that we are planning to test run this much more in a higher scale. First, we want to run those virtually, like the one that we did here with large data sets. And then we want to run that in practical data sets, practical devices like actual Raspberry Pis, Arduinos, or smart devices, and Amazon Echo, and see how it goes. And also, another target is that to develop a library which can be used with the NDN. We will prefer initially a Java-based library because we are really good with Java, and that's basically our so for future work. Another very important thing that I missed is basically improving the agent performance. There are thousands of techniques out there. We haven't tried all of them, and it's not we're not going to try all of them, but we will be able to significantly improve that if we do much more research on this one. That brings us to the end of this presentation. Thank you very much.